Hello, everyone. I'm Jianan Hu, the current postdoctoral researcher in Oxford. It's my pleasure here today to share with you a simple story of part of our postdoc project with Mitsubishi Heavy Industries in Japan. Three keywords: rupture, dissimilar metal interface, and cohesive zone modeling. I will briefly introduce the project, then the modeling of different parts, followed by simulation, a simple simulation, finally the conclusion and future works. As we know, the welding component has different parts, like weld metal, heat effective zone, and parent or base metal. And heat effective zone can be even complicated by dividing into different regions, like these parts. There's a growing interest in dissimilar metal technology because engineers can take advantage of integrated properties of different materials, especially when the components used at the multiple environmental conditions. And this also provides more options for engineering designs. This figure here shows P91 welded with ferritic P91 with austenitic stainless steel. It's a very common dissimilar metal weld, and often filler metal is used between two materials as a buttering layer between two materials. And two purposes of this. First, this is to ensure the mutual solubility between the two materials. This is very important for the welding quality. And second, normally the buttering layer can help reduce the residual stress that can be potentially generated during service in high temperature. So in our project, I can say our sponsor, MHI, they are interested in P91 welded with P22, two ferritic steels. But since Inconel has an austenitic structure, here we have two ferritic austenitic interface. A lot of uniaxial pre-rupture tests has been done on this type of dissimilar metal welds when at least one metal is P91. Here is a collection of the failure modes of the test. I classified it into three. Type 5, which failed at base metal, type 4, which failed at heat the affected zone, and type 6 or 7, which failed at interface. Here, type 7 refers to the failure exactly along interface, but type 6 refers to where the crack initiates at the interface, but at the last stage, it diverts into heat affected zone or parent metal. But here I classify them together because the last stage only contains a little influence on the line. So all these failure modes have some relation occur in the ferritic and Inconel side. No matter what the other metal is, here the other metal is austenitic stainless steel or nickel-based alloys. And in our project, we are focusing on the interface failure mode at 550 degrees C at higher temperature, higher rate, sorry. So some data of P22 welded with another material has been done by Laha Group in Indira Gandhi Center for Atomic Research, or called IGCAR. And here's a collection of the P91, P22 dissimilar metal welds data with rupture life. And we can find several features of this. First, dissimilar metal welds has a reduced life compared with pure metal as a given applied stress. Second, the interface failure mode compared with other modes has a change of slope here. And the third, P22 dissimilar metal welds has a shorter life than P91 dissimilar metal welds. And finally, although it's not shown in this figure, but all the failure mode has been predominantly occurred at the interface, at the ferritic austenitic interface. So the the goal is to use some simple model to simulate the interface failure and understand what is going on at the interface. And the ultimate goal of the project is to propose some simple physical models that can capture the essential physics that happen around the interface and to use it to evaluate the problem. So the tool we are going to use is cohesive zone modeling, and it's a very powerful tool if you know the potential crack propagation path. So the framework is based on the virtual work principle, the work done by the actual stress on the body, plus the work done by the traction on the interface or the cohesive zone here, equals the work done by the external load. So this framework can be easily embedded into Abacus using cohesive zone model in the user-defined element library. And here, BC is the shape function of the cohesive elements. If you have defined the design element, this is already known here. And basically in the UEL, we need to provide what is traction and how the traction evolve with separations. So this is a model we find in Abacus. The two materials with the corrosive layer or interface zone. And we calculate two systems independently because we want to understand what is going on for each simple case. And the problem is uniaxial loading at 500 degrees C and with thermal elasticity plus creep. And here at this stage, we don't consider heat like the zone, but just base metal and the interface zone. For bulk elements, we use the standard isotropic elasticity and standard power, steady-state power law creep model, and isothermal expansion. Definitely, for different materials, we have a mismatch in the thermal and elastic properties. But here, I just want to highlight the mismatch in creep property, which is very important in the result, which I will show later. Here, you can see the mismatch between creep properties is very large or much larger between P22 and Inconel than P91 and Inconel at a given stress. And for cohesive zone, we'll use the cohesive elements, which are two-dimensional four-node linear cohesive elements, and all the displacements at the node are given by Abacus, and these can be rearranged to calculate the separation or separation rates at the interface cohesive elements. And for the cohesive zone or cohesive constitutive laws, we use this here. We have normal direction, tangential direction, and for each direction, we have elastic part and creep part, where A, B are just constants. And omega here is a Kirchhoff type damage variable, which here for the problem we're looking at here is like a mode 1 fracture. We simply assume the damage is a variable is defined by the creep separation divided by the critical value. So omega can be from 0 to 1, and it fails when omega is 1. And this model is being implemented in Abacus UEL using Newton-Raphson duration. So the first step of the simulation is a mesh sensitivity study. We decided to choose the criteria of creep crack propagation. On the interface, we deleted several elements at the edge to initiate or to create a crack. Then we selected some parameters to do the creep crack growth test. But these parameters are random because we haven't calibrated these parameters with the data, but they are not random to some extent because the order of magnitude should not be random. So we can see here the 200 cohesive elements along the interface could give a reasonable result. So in the simulation, we have selected the 200 elements along the interface. And during the calibration, we fix the elastic constant because the big influence will be given by the creep part. And T0 is a reference traction here, which is a constant. We just select 1 megapascal. Then we calibrate the creep constant, delta C, and M. So the calibration contains 2 parts. The first part, if we look at this data again, so the first part is an analytical calibration. If we think the traction along the interface is uniform, then the interface will fail at once when omega is 1. Based on this, we can write the evolution of the omega in this way. Here we ignore the T0, which is 1 megapascal. Then we can rearrange this by understanding that omega is from 0 to 1. And the type is from 0 to TF, which is a failure type. Then we can do the integration and rearrange into a log-log plot. We can obtain the value of M, and this is the intersection, which for the 2 materials, for these 2 lines of data, we get these. Then in abacus, we fix the slope of M, but calibrate these parameters here. Then the video. Okay, so this is the video just to show you the simulation of the result, which you can see the initiation of crack at the edge, then gradually propagate towards the center. And I chose, for each case, I chose just 1 stress to illustrate the result. So this is just some visual effect. It doesn't mean anything because you can't see the quantitative result of all of this. But you may ask why the crack starts to propagate, but it doesn't penetrate the whole interface. That's because it's getting harder and harder for the convergence. You need to reduce even more for the time step to make it converge and to move forward. But for engineering perspective, there's no use because even if you reduce the time step, you can get a very nice visual effect of the result, and you can see the separation of the 2 blocks. But that doesn't change the part of the result. So this is the final results, and the calibrated parameter of these 2. And I also plotted, or I also have done the results using 400 cohesive elements, which you can see the 2 type of the simulation, very similar result, and they are very close to the experimental data. And another thing I found in the simulation is these 2 parameters can be served as 1 fitting parameter, which means abacus is not sensitive to the detailed value of these 2, but it's sensitive to the ratio of these 2 parameters. And here I showed the crack propagation for these 2 examples. This is P22 dissimilar metal welds, this is P91 dissimilar metal welds. And you can see the very important feature here, where more time in P91 dissimilar metal welds has been used to initiate a crack. You can see here when it starts, then when omega is 1 is here, the already time is roughly 3500, which is very close to the failure time. Then for P22 dissimilar metal welds, the crack initiates at a very early stage, and more time for this dissimilar metal weld system is used on the crack propagation. Another thing, you may see, oh, this is not symmetric. Again, you can see from the simulation, abacus simulation. That is because if you still in the damage accumulation process during the simulation, it's very sensitive or to the numerical perturbation. That's why you see some asymmetric result here. But what's causing these two, the difference between the two systems? Remember I told you the creep mismatch of the two systems. Oh yeah, good. So the main cause is due to the creep mismatch between the two materials. The larger the creep mismatch between the two materials is, the more likely the crack will initiate at the early stage. And the conclusion, so we have simulated the creep rupture interface failure mode in the two dissimilar metal systems at 550 degrees C. And we use the interface cohesive zone modeling with Gaetano type damage in Airbus UEL. And the result of the two systems is like the VRGs. I don't repeat this. But this is the report for the two materials. This is not the take-home message. The take-home message is difference in the captured damage accumulation of the two systems is attributed to the mismatch in creep properties between the two materials. And finally, the ongoing work of visual perspective. So we haven't considered heads in the material, and later we will consider if you have a different property in the heads surrounding the interface, what will change for the simulation and frame life. And second, you cannot guarantee the weld angle as perpendicular to the loading direction. So there may be some different angles. In that case, the tangential traction will take into effect. So we need to consider the interaction between the two traction. Then the multi-axial and cyclic loading, where the plasticity will have some effect on the reduced stress. And finally, the physical microstructure model. And just to show some figures, that the particles around the interface is very important, which has been shown to be associated with the cavities. So the physical models, we're going to model the precipitation and cavitation, nucleation, and growth. Thank you for your attention.